where? Okay, here's where we were. I got it, man. Can somebody get rid of that thing on? I got it. Okay. What on earth? All right. It definitely made sure that we got it. Everybody of you know, now you know that you have been recorded, you're being recorded, right? So here's where we were. We train a network by minimizing a loss, right? So who's number 42? One of you got the number 42. Who is number 42? So how did we define the loss? The average divergence over the training sample. And so who is number 77? What is this supposed to represent? The expected loss, right? So, and who's number 4? One of you is number 4. Who is number 4? Yes, okay. We said that the loss is an unbiased estimate of the true objective. What did we mean when we said that? Okay. Does anybody else remember? What do we mean by saying that the loss is an unbiased estimate of the true objective? Yes. All right. They have the same expected value. So how many of you actually watched the second part of lecture 5? Raise your hands. Right. We went over that. So Sanika, how did we explain that in the lecture? So how did we explain what was meant when we said that the loss is an unbiased estimate of the true objective? Yeah, so we said the two were one was an unbiased estimate of the other. What was the reasoning behind it? Okay. Anybody else want to guess? Linearity of expectation, but we actually had an explanation for that. Okay. We made a statement about the variance of the loss, right? And does anybody remember what we meant when we spoke about the variance of the loss? Anyone? Okay. The loss is a function of two different things, correct? What are these two different things? Can anybody remind me? Pardon me? Weights and training data set, right? So how many of you realize that the loss is a function of the training data set? Raise your hands if you realize that, right? If I change the training data set, will the loss change? Can everybody say it aloud? Yes. Thank you, right? So now, if I have many different training data sets, so if I actually write down the loss is going to be, I can get a chalk. The correct way to think about the loss is like so. It is the loss of W, training data set, right? As I keep changing this training data set, if I change the training data set, I assume that the training data set is the same every single time, right? I mean, the set size of the training data set is the same every single time. I have n training instances, but the samples I'm using for training change from from function to function. So I have L of WT1, L of WT2, L of WT3. All of these are going to be different, correct? If I took an incredibly large number of these functions, where all of them differ only in the training set, what is the average of all of these functions going to be? Anyone want to tell me? Who is number 36? Yes.
Maybe it was the estimate, distribution of
Is it an estimate? If I take a very large number of these functions where it's always the same loss, the only thing I'm changing is the training set. and I take the average, what will that average be? So anybody else want to tell me? Yes, Philip? It will converge to the expected divergence of between the network and the desired function, right? So given the same thing, so I have all of these. This is a very large number. The expectation is going to be E of dive, right? Are the guys on Piazza on Zoom able to see the board? Okay, right. So now, when we spoke of the variance of the estimator, what were we speaking of in this case? Anybody want to hazard a guess? Anyone want to hazard a guess? Okay, can you tell me which of these you really want to minimize? This one or this? Can everybody say this aloud? The one on the right? That's not loud enough. Say it again. Yes, I'm going to make you do that. Just make sure you're engaged, okay? So the point is we are sort of minimizing the functions to the left, one instance of the functions to the left. And we are hoping that when you minimize this guy, this one too is minimized. Correct? But then this one is not going to be the same as this. Each of these is a different function depending on the training set you got, right? How do you quantify the difference between this term and this term? This is a random variable. Depending on the training set you choose, it's going to be different. Correct? How would you quantify the difference between this and this? Anyone? The variance, right? The term to the right is the expected value of all of the things to the left. And the variance is going to tell you how far it is likely to be on average. And so do you want the variance to be large or small? Because when it's small, you're much more likely to be minimizing the correct function, right? That's where the whole discussion of the variance came from. This is for those of you who asked on Piazza. Anyways, going on, we minimize our loss through gradient descent. Batch updates must process the entire training data before each update. Incremental update rules will update it after individual steps, right? And after individual instances or mini batches. And because the loss function varies from instance to instance, from mini batch to mini batch, the derivatives are likely to keep swinging around. So you need trained algorithms to smooth things out, particularly when you're having incremental updates. So we're going to go on. We're going to talk about some other characteristics, things that will help us. First, again, guys, I'm likely to go over today. So if that happens, I'll finish the class in the evening. I apologize. You're still getting used to the technical issues over here, right? So in particular, we were expecting somebody from the Eberly Center to give you, make an announcement. So they will do so hopefully in the next class. We're recording you guys. We are going to keep track. We will need your permission. But one of the things we want to do to improve the class, we keep trying every single time, is to sort of compare your performance to your background, which department you come from, what background do you have, things like that. That's information I do not have, the Eberly Center has. And so we want to go through that whole thing to find out which groups are performing better, which are performing worse, so that we can improve our delivery. As Judge? It's a, yeah, this is just a random variable. It depends on the training set, right? So if I took an incredibly large number of these, if I took infinite different training instances of the training set, the average of all of those guys is going to be in the limit, basically the same as the true objective. So again, at 6 p.m. today, we will complete today's class. I apologize, but that should be short, 5 or 10 minutes. Okay. So now here's where we've got what we've got. We have the loss. The loss is the average of the divergences over the individual training instances. This is what we are going to minimize, right? Now, for this to actually, for us to be able to minimize this properly, we want the loss to be a nice function, right? What do we mean by a nice function? Can anybody tell me? Yes. Convex and differentiable. Pranav, you had a quick answer? Same thing. Can say number 16. Who is 16? How would you say it? Differentiable, right? So at the least, you want the loss to be differentiable. Differentiable with respect to what? Yes, what do you want it to be differentiable with respect to? Pardon me? The network parameters, because that's what it's a function of the network parameters, the rest are fixed, right? So you want it to be differentiable with respect to the network parameters. Now your loss can have two different shapes. You could have a loss of this kind. You could have a loss of this kind. You could have a loss of this kind. What two? You can have many different shapes. Or is there an eraser here? Yeah. You could have a loss, say, of this kind. So you have 1, 2, 3, 4. Clearly, this is nasty. This is not a very good loss. So let's ignore this, right? This, you agree, is also nasty, right? Or anyway, of these three, which of these do you think is going to be the most useful loss function? 1. Why? It's convex. What is the advantage of convexity? So both of them have global minima, right? What is the advantage of convexity? There's no guarantee that it will have a closed form solution. Yeah?
There's only one local minimum.
Both of these have the same. Both of these have just one local minimum. Faster gradient descent. Well, yeah. Both of them have a zero gradient in one spot.
Same step size to get to the minimum faster.
Are you sure? So for the same steps, there's a different property. When you're far away from the optimum, do you want to take large steps or small steps? When you're close to it, what do you want to do? Why? Convergence, you can overshoot. Which of these is going to give you the appropriate behavior? The first one, right? You want the function to become flatter as you approach the minimum, and you want it to be steep far away. The second function is not a good function, right? So now, using this, here we have three different kinds of loss functions. The first one is useless. Both the second and the third have a unique minimum. The derivative is going to be 0 at the minimum. But the first one is not going to be very nice, because as you keep stepping along, in the beginning, when you really want to be rushing, you're going to be taking tiny steps. And then as you approach the minimum, you begin bouncing around and swinging away. So this is not a very nice function, right? This is the kind of function that you really want, at least in the vicinity of your minimum. That's when you're going to approach it smoothly. Now, we looked at two different kinds of loss functions. The Kullback-Leibler divergence, which is a statistical estimate. It compares two probability distributions. We saw what the KL divergence looks like, right? But then why did we choose the KL divergence and not the L2 divergence, which you could also have used? Remember, just because you're performing classification doesn't mean you cannot use the L2 divergence. You have a one-hot output, and then you have the output of the network itself. You can always compute the L2 divergence between the two, right? So why did we choose the KL versus the L2? Yeah. Convex with respect to? Yes, right. Yeah, guys, I'm assuming you're giving me the same answer, right? So here's what it looks like. This is the L2 divergence. This is only with respect to the weights of the output layer of the network, okay? If I have a softmax output, then with respect to the output weights of the output layer of the network, this is what the L2 looks like. It looks like the flower that we said was not a very nice function, right? This is what the KL looks like. It's a nice, pretty ball. Does this mean that this is still going to be convex with respect to the weights of the lower layers? Yes or no? Can I say this? Can I hear everybody say it? Yes or no? Okay, right? But this is at the least, it's at least convex for one layer. So given a choice, which would you choose? The KL, because at least for the final layer, it is convex, right? So yeah. Because when you go further down, the function becomes a lot more complex, right? You have sigmoids of sigmoids of sigmoids, or ReLUs of ReLUs of sigmoids of ReLUs of ReLUs. The predictive, you cannot guarantee anything below the first layer, the output layer. Yes. That's at the output in the comparison. Yes, that's a good one. But in terms of the bowl-like behavior, this is the key one. Yes. So that's with respect to, this is with respect to the parameters. That was with respect to y, right? And y is a function of the parameters. Yes, what's the question? What we mean, so you have a network where the network is going to be, you have new layers and layers and layers, and they're all connected any odd how. And then finally, at the output layer, you're going to have weights, and then you have a softmax, and then you have a y, and then you compute the KL divergence. So what we mean by that is that this KL divergence is convex with respect to the parameters out here, but there's no guarantee about what it is like for the parameters further down. Yes.
Network, the less that impact matters.
Pardon me?
The more layers you have, the less that is an impact that.
Just not being, it's going to matter even more because you're back propagating, correct? So if you're back propagating, what happens? If your derivatives are getting killed right here at the very first layer, as you're going back, what is going to happen? Then there's nothing happening. You want, when as you go further down, you want it to be more and more bowl-like, just so that the derivatives can go backwards, correct? Everybody with me so far? Questions? So I think, by the way, here's a little note on derivatives. This is something that you might have encountered in your homeworks. When I'm performing regression versus classification, yes, am I?
So does any kind of activation allow the gradients to propagate better? In particular, as far as this
I think to the best of my knowledge, the ReLU is the only one that has those properties, ReLU or its equivalents, because it has the slope of 1 pretty much everywhere. But then once you get into the flat regions, it's not going to propagate anything. But if you look at we'll actually get into that later in a few lectures, several lectures down the line. But remember this question, it's a good one. Okay. So if I'm performing regression, in a regression network, what is the output activation? What kind of activation would you use if I'm trying to predict real valued numbers? Pardon me? There will be, it's just going to be an identity function, right? You compute a weighted sum, and that's going to be a regression. If you're performing a classification, then who's number 27? What kind of class output layer would you have? Softmax. And what is its output going to be? Pardon me? No, is the output of a softmax 1 hot? No, what is it? It's a probability distribution over classes, right? Now over here, y equals z, here y equals softmax of z, correct? In the first case, you would be using, when you're performing regression, you would be performing typically be computing the L2 divergence, which is defined as half of the squared norm, correct? Now, if you take the gradient of the divergence with respect to the affine term z, okay, not the output of the activation. In this case, the output of the activation is the same as the affine term z. Then the derivative, it turns out, you can just work it out, is just the difference between the actual and desired outputs of the network, right? And you can see, so now this is squared. So why is it y minus d and not d minus y? Can anyone tell me? Without going through the math. Can anyone tell me? Okay, if y is lesser than d, is y minus d going to be negative or positive? Negative. In that case, what is gradient descent going to be doing when the derivative is negative? Is it going to be increasing the value or decreasing the value? It's going to increase y, right? If you flip the sign, would that happen? No. That's why it is y minus d and not d minus y, intuitively. Is that making sense to everybody? Raise your hands if it is. It's got to be very clear. You have to think about the mechanics of it. What is gradient descent going to do at each step? Now, here is the other thing. The square is an absolute value, right? So anyways, so now if I have a softmax and if I'm performing classification, and I compute a Kullback-Leibler divergence, and I take the gradient of the Kullback-Leibler divergence with respect to the affine input to the softmax. I'm not speaking of the gradient with respect to y. I'm speaking of the gradient with respect to z. Here's something magical that happens. Even in that case, the gradient just ends up being the difference between the output of the softmax and the desired output. So here, in this case, the gradient with respect to z was, in both cases, the derivative is the difference between the output of the network and the desired output. The math is fairly straightforward to do. And this is why in your PyTorch, you have a softmax cross entropy. That's because they just mush the softmax into the cross entropy loss function itself, so that you can just compute y minus d and give that as the gradient going backwards. But in reality, when you actually have a network, is the softmax part of the network? Probabilities, right? So never confuse the engineering solutions with the actual math. The key piece is, in both cases, the gradient with respect to the affine value just before the output is going to be the error, okay? And it's for this reason that backpropagation is often called error backpropagation. You're always backpropagating errors, okay? 2 poles. On Piazza. Time. No, not that. Yeah, I know. I'm going too slow. I'm at least 15. Okay, I'm giving you 15 seconds, guys. Yes. The math can, you just ask on Piazza, we'll show you the math. It's very straightforward. Okay. All right. Okay, we're done, guys. Here are the poles. Only the KL is convex with respect to the weights of the final layer. And for most popular networks, you're going to use the L2 loss if you're performing regression, KL divergence if you're performing classification. In both cases, the gradient of the rest network with respect to the affine value, as we just saw, is going to be the error. Okay. Now, how can we actually, story so far? Gradient descent can be sped up by incremental updates. Convergence can be improved using smoothed updates. The choice of divergence is going to affect the results. If your divergence is a nasty divergence, even before you begin backpropagating things, you're going to get stuck. So having the appropriate choice of loss, at the least, you want the loss to be convex with respect to the parameters of the network, right? Okay. Now here's the other problem, batch normalization. And this is where you guys really should have gone through the handout. If you had gone through the handout, batch normalization would have taken me 20 minutes to explain. Now it will take me an hour. So I have a choice. I can rush through this and do the rest. Okay, now let's go through it. Okay. Now here's the assumption that you're making, right? When you're training with mini batches, every single mini batch, you expect every single mini batch to be representative of the entire training set, correct? Will it really be? So what's going to happen? This is the assumption you're making, that if I look at all of my mini batches, they're kind of sitting on top of each other wherever I am. What you will actually see is something like this. Each mini batch is shifted with respect to the other mini batches. You have a covariate shift, things that vary together, right? And this can occur anywhere, because as your data passes through the network, different regions of the data keep getting moved around. So data points which seem to be lying very close to each other in the input, by the time you get to the fourth layer, they could be very far apart. And so even though your mini batches appear very similar at the input, at the fourth layer, they could end up like this or even like this, right? So, but how do you want them to be? You want them all to be lying on top of one another, right? This is clearly showing that the mini batches are not representative of overall distribution of the training set, let alone the entire data. So our solution is we want to take all of our mini batches and move them into a common region of the space. We want to shift them to a common region and adjust them so that they have a common set. The problem is where? What is that location that it's really got to be in? Because the location depends on many factors. It depends on the data, but it also depends on the processing that has been performed by the network until that point, correct? Because the network is moving data around. And so now we have this problem. During training, for each mini batch, we want to account for the fact that they're all scattered, and we want to sort of normalize them so that they move to a common region of the input space. And we don't know exactly how. And the shift that must be performed for each mini batch is going to be different. That is a problem as well. There are 4 unique arrows, right? We're going to simplify that. What we will do is first, we will move all of them to the origin. Every single mini batch is first going to get moved to the origin. We're going to normalize them so that the mean of the mini batch is 0 and the variance of the mini batch is unity. And then once they're there, they're all in a standardized position. Each mini batch can be shifted to this location, right? So is this process, is the visualization of the process clear to you guys? Questions? Blaine, did that make sense?
Yep.
Any of the rest of you guys? You're whitening each individual mini batch and then moving it to the common location. Correct. Yes, Ruchi. Standard deviation is the spread. So the standard deviation, when I move it to the center, I'm normalizing it to have a 0 mean and unit variance. So along each component, here, right, this is actually going to be one number. I'm just showing you a blob. That is going to have a variance, even after I cancel out the mean. So that the square root of the variance is the standard deviation. Dividing by that is going to make sure that the spread is 1. Right? Any other questions? Yes. Pardon me? So basically, what the point is that data are being moved to different regions of the space by the network. We don't know exactly where, so you want to maintain the distinction. So if you actually didn't do that, you could try that. It's easy enough to eliminate this from your batch norm and see what happens. Right? Yeah. So can you ask that question aloud, please?
And remain their labels unchanged. Are we like change the training set and this will
the training set is clearly being shifted around, right? You're right, but you can think of this as normalization. The normalization is accounting for local variations in the data that helps it generalize. But that's a valid question, right? Oh. It's a simple poll, guys, 10 seconds. Yes, Amay? Yeah. Not the inputs, the value at any particular node, any node, okay? So batch norm accounts for covariate shifts between mini batches. This is basically what we said. Each mini batch can have a different location. We want to normalize those, all right? So now let's look through the math of batch norm. Here's what we are going to do. I want you to remember that you're actually operating on entire mini batches of data, and you already know how this is done. You've gone through the mechanics of it in your homework. Most of you have. And so let's take a look at our old representation of a network. Where batch norm is going to be applied typically is out here. In each neuron, we perform a 2-step operation. First, we compute an affine function of the inputs of the neuron. Then we apply an activation to the output of this affine function. So in between, there's this affine value z, which has been computed as a function of all of the inputs of the neuron, right? Mini batch normalization is going to be applied right there. The little yellow box, which is the BN operation, which occurs between affine function and the activation. So how exactly is it performed? Everything over here is now being performed over entire mini batches. So this represents a single input, but then over a mini batch, you'd have many such inputs, correct? So from a single input, you're going to get a single z, which is an affine function. Now that affine function is now going to be put through your batch normalization operator. And we said the batch normalization was a two-step process. What were the two steps again, Charlie? Pardon me? Okay, so who's number 42? 42, as we know, is the answer to everything, so he can answer. Okay, so this is the two-step process. Is first you shift the data to a in a manner such that over the mini batch the mean is 0 and the variance is unity, correct? And then the second step, you apply an activation to it. Now, so what is the actual procedure? The first thing you do is you compute the mean of the z values going in. And then you compute the variance of the z values going in. This is the variance and the mean computed over the entire mini batch. And now to center the mini batch, we are first going to subtract the mean and divide by the square root of the variance. So the first thing you do is this intermediate step u represents the centered data. To get the centered data, what would the two steps be, Kira?
The centered data for each batch.
Mm-hmm.
Take the mean 0 and then
So what would the operation be?
subtraction and division.
So you would subtract the mean of the mini batch and divide by the square root of the variance. The plus epsilon is just to prevent division by 0. Yes.
In the most extreme case, let's say your mini batch is 1. It's just one size. Then every single input get in.
We are going to get to that by the end. You're right. Okay. Hang on to that thought and come back with that thought at the end of it, right? And then once this u has come, that's a good question. Okay. Once the u has been computed, we are going to be operating on the u. And the way you would do it is you're shifting it to a new location. So to shift it, you're going to do two operations. First, you scale it so that there's some standard spread. You scale it by some term gamma, and then you add this constant beta, which moves it to the new location, right? So this is going to be the operation that you would perform to move everything to the new step. So first, you compute the mean and the variance of the mini batch. Then you normalize the mini batch to 0 mean unit variance, and then shift to the correct position. This is the entire operation going forward, okay? I can redraw the picture in this manner. Yes, Sammy? That's just to prevent division by 0 for the same reason that Joe mentioned. Sometimes the variance can go to 0, right? So so here is the two-step process. I can think of it this way. U is the outcome of centering. And then after the centered data has been obtained, you scale it by some gamma and you apply some beta, okay? Now, looking at this process, can you tell me, do I need an extra bias term in my affine function over here? How many of you think that this needs an extra, that the z must be an affine function and not a linear function, as we always have done? Do you have an opinion on this? Raise your hands if you have an opinion on this. Okay, what's your answer? So the point is, if you had a constant term going in, that's going to be canceled out, right? So therefore, is this making sense to you guys? It makes no sense to have an additional bias term over here because centering is going to cancel it out, right? So when you're applying batch normalization, you do not have bias term. But there is nonetheless a bias term. Where is the bias term? Can everybody say it out aloud? Thank you. Right. I like that. So, pardon me? It would just, it would just get cancelled. It would just be removed. There's no point, right? It's an arbitrary thing. So anyway, now this little operation that we are performing during training really screws up training. Why would it screw up training? Does anybody want to take a guess? Why would it be complicated?
Because you've shifted the input and you're calculating the errors based on your input, but now you've shifted the input.
The shifting is also it's a known function, right? Yes. You're relying on multiple instances. This really screws up life, right? When we perform backpropagation originally, were we considering one training instance at a time or looking at batches? One training instance at a time, right? So guys, if you're not listening to me, I'm going to make you scream things aloud. So just keep, right? So we're always backpropagating one training instance at a time. That cannot be done over here. And the reason for that is in your standard training, your mini batch loss is the average divergence over all of the instances in the mini batch, correct? And the divergence for any individual instance only depended on that instance because the output of the network only depended on that instance. Now what happens? So you could just, compute the derivative trivially. But now what happens is this divergence, the output of the network depends on the mean and the variance because every training instance in every mini batch has the mean being canceled out and it's being divided by the variance of the mini batch, right? And so for any given training instance, the output depends on the mean and the variance, not of the global data, but of the specific mini batch that it had the misfortune of occurring in. This making sense, right? And so as a result, I cannot simply compute the derivative with respect to just xt. I have to consider mu and sigma squared, which are also functions of xt, right? And many other terms. And so this causes grief. To give you an explanation, here's what happens. Now I'm looking at the orange box represents the batch normalization operation. This is not the neuron, right? So these z's represent all the affine terms for a mini batch. You have many different instances in the mini batch, and each one is going to have an affine term z. This entire collection goes into this box, and then out comes the batch normalized z's, right? That's what goes into the final activation function. So, but anybody remember, Thomas, what was the difference between a scalar and a vector operation? The way we defined it. Pardon me? Yeah, so, but what is the difference? Key difference? Shubham, what was it? So basically in a scalar operation, every output considered only the corresponding input. In a vector operation, any single output depended on the entire set of inputs. Is this a vector operation or a scalar operation? This is a vector operation. Every single output depends on every single input. Here is the real picture, right? So what happens? Now, again, how many of you recognize this kind of diagram, guys? It was there in the pictures. Yes, thank you. There are two people here who've been kind enough to go through my handout. So there are two variables, mu squared, mu and sigma squared, right? And so every one of these z's influences mu for the mini batch. This is the standard influence diagram. And the variance, what is the variance dependent on? So Rahul, what is the variance dependent on? And okay, who's 60? Who's person number 60? Someone has yes. What is it dependent on? Influence. What is the variance influenced by? So I have a very conveniently put the picture on the screen, right? So I never ask you a question where I haven't presented the answer on the screen. So I have all of these z's. They're all influencing sigma squared. Sigma squared is also being influenced by me, right? Now, what about the individual u's? What is any given u being influenced by, Alex? So specifically amongst the variables over here, what would you pick? So does anybody else want to answer that? Yeah. Yes. Yeah. A single u is dependent on the corresponding z and the mean mu and the variance sigma squared, correct? So that's, you see the arrows over here. Now, once you compute the u, the activation is low. Each activation is, each instance is locally being operated upon, right? So everybody clear with what is happening over here? Now, if I'm performing back propagation, what happens? I've got the output of the network. And from here, I've sort of computed the derivatives of the loss for every individual training instance. So for each training instance is going to have its own loss, correct? And the global loss is the average of all of these losses. So the loss, mini batch loss is the average of all of these losses. So when you're performing the back propagation, you'd have computed the derivative of the mini batch loss, which is the average loss over the entire mini batch with respect to every one of these things, right? Because you're operating the mini batch as a unit. Then once you've got the derivatives over here, what is the next derivative you would compute? Who's number 55? Who's 55? Yes, what is the next one you'd compute? I've got the derivatives for z, z hat, which is the output of the activation. What is the next one I would compute? This is the output of the, actually wait, this is the output of the scaling, right? So what is the next thing I would compute? It would be the derivatives with respect to the u's, right? So when you're going backwards, so here are the forward operations you've performed. When you're going backwards, you would have computed the mini batch derivative of the mini batch loss with respect to y. Then you would have taken a step back and computed a derivative of the mini batch loss with respect to the output of the batch normalization, which is z hat, right? And then thereafter, you want to compute the derivatives going back, okay? Now for any single instance, you have this equation which says any single instance in the mini batch z hat of I equals gamma ui. Is that how we call it? Beta, right? So I have the mini batch losses for the entire, the derivatives of the mini batch loss with respect to every z hat in the mini batch, okay? So who is 92? What is the derivative of the mini batch loss with respect to gamma? Pardon me? Of the mini batch loss. The sum over I, okay, and ui, what is ui? I want the derivative, okay, somebody else, who's 84? Who is 84? One of you is 84. What is the derivative of the mini batch loss with respect to gamma? Guys, wake up. This was a very easy one, right? It doesn't get easier than this. Then it's going to get harder. Who's 75? Who is 75? You're 75? Okay, so what is that? You don't know. Okay, tell me. Tell me, Rami. Yeah, you. There's the 1 over b over here, but you're missing the d loss over d z hat I times ui. Isn't it going to be that? Right? How can you guys miss that? Come on, right? You have the entire mini batch, so you're going to eventually get the derivative of the divergence with the mini batch loss with respect to gamma, right? Can somebody tell me the derivative of the mini batch loss with respect to beta? Okay, yes, Varun, tell me. Can you say it aloud, please? It's going to be, this is going to be d loss over z or z hat. Okay, which z hat? I and sum over I. This is going to be the derivative for this guy, right? So these two are easily computed. No biggie, right? So if I do that, I now have the derivative with respect to b. I can just, these are the parameters. These are for individual instances. I have to sum over the entire mini batch, but we are fine. Okay. Now, my next question is for any individual u, what is the derivative of the mini batch loss with respect to an individual ui? What will it be? Who's 52? You're the answer plus 10. So tell me. So for this guy, so the derivative with respect to ui, d loss over dui is going to be d loss over d z hat I times gamma. Everybody with me so far? Raise your hands if you got this. I want to see everybody's hands raised. Yes, if your hands are not raised, I'm going to wait till you raise your hands. So please raise your hands, everyone. All right. So this is good, right? We have managed to figure out in this process the derivatives with respect to all of these guys. There has been no confusion over here. Where is the real grief concern? It's going to come out in taking this derivative back to z. Okay. And to see why, first let's answer these two polls. Ten seconds, guys. Okay, Michael's done. I can move on. All right. So in batch norm, the issue is that the normalized value ui for any given zi depends on all the other zi's in the mini batch. This is the issue, right? The rest of the statements are not really true. And for the second one, batch norm is really a vector operation, right? It operates on a collection of inputs and produces a collection of outputs. If you vary any input, all of the outputs are going to change. So this confounds our math for computing the derivative. So here is the complete dependency diagram for the batch norm, right? Now, are there any brave souls out here? Can you raise your hand if you're brave? Can I anoint someone as the brave one? Did you just raise your hand? Okay. So thank you. You are indeed brave. All right. All right. Can you help me derive the basic derivative rules for derivatives over here for any single term? So let me think of this. I have zi, z1, z2, and so on, zn. All of them influence mu. Then all of them influence sigma squared. And then these two influence u1, right? I want you to tell me what the derivative rules would be for u1 with respect to z1. Yeah, so how, if I had to write the formula down, can you just give me the breakdown? How many input components would I have for the derivative?
3.
Okay, what would those be? So this, so first, am I looking for a partial derivative or a full derivative of u with respect to z1? Partial? Full. Okay, there were only two answers. Very easy. Okay, so this is what I'm looking for. What are the three components? Okay, okay. So what would that be? So can you write those things down for me? I have.
So the derivative of u with respect to the standardization
Okay.
and the derivative with respect to
This partial again. And
derivative of u with respect to
zi. So this is a partial, right? This is the derivative going over the vertical branch. There are terms missing over here. What are missing? Yes. I need to go all the way from u to z, right? So what is the term missing in the chain rule? Yes, Jim. D sigma squared over d z1 zi d mu over d z1, right? So everybody get what we just did. If you got that, raise your hands, right? Even if you got your laptops open, right? Thank you. So, you know, we should give her a hand. Not everybody is brave, please. So, all right. So this is what we have. The complete derivative of the loss with respect to any given zi. If I want to write this, here is what it looks like, right? The derivative of the loss, every u is influenced by every z, right? So because every u is influenced by every z, this is, I was just looking at the derivative of a single u with respect to a single, but in the bigger picture, if I change any single z, every single u is going to change. And every single u is going to be affecting the mini batch loss. So if I'm going backwards, my derivative of the loss with respect to any z has to sum over all of the u's. Everybody with me with that? If you are, raise your hands. Okay. I'm sorry, this is one way of making sure it registers. If nothing, you'll remember raising your hands. Okay, so the way I would have to do it, I'd have to sum over all of the u's. Again, this is the dependence diagram, right? So what I have is z1 influences all of the u's, u1 through un, and all of them influence the loss. And so according to the equations that the pictures and the dependence diagrams that we've drawn before, that the derivative of L with respect to Z1 is going to be the sum over all the U's of the derivative of L with respect to U times the derivative of U with respect to Z, right? And we assume that we already have the derivative with respect to all of the U's at this point. So the thing to compute is this guy. This is already present. This is the guy that we need to compute. Now let's try to compute it, right? Here are all the rules that we want. You knew that the mean is a function of all of the inputs. It's just the average. The variance is a function of all of the inputs and the mean, right? And u is going to be z minus the mean divided by the standard deviation, square root of the variance. I'm going to use the variance as my variable, not the standard deviation, because it's much more convenient mathematically, all right? So this is the variance raised to negative half. Now the derivative of u with respect to z, as Kira rightly pointed out, has three components. This is the full derivative, right? Okay, who's number 49? What is the difference between a partial derivative and a full derivative? Okay. So that's the textbook definition, right? But can someone give me a better definition based on this picture?
Only look at the perturbation caused by one particular parameter or
Look at the picture. Malini, can you help me? Anybody else give me, the picture is up there. Can you tell me? Yes.
The top line,
The
Z1.
partial or the full?
That's the partial.
Partial.
It's all of the influences connected.
Exactly. So the partial derivative over here is just, the guys on Zoom can't see my, there's a pointer, but it's the line connecting U1 to Z1 directly. That is the partial derivative. What is the local influence of U1 on Z1, right? Not considering the influence of U on the remaining terms. But then if I perturb U, it's going to change everything else in between. And so all of these guys in turn are also going to affect U. And so the full derivative combines all three terms. Everybody clear? Thank you, right? So this is what it's going to be. This derivative is going to have a partial component over the direct link. Then it's going to have this link. The derivative, again, this is because U has only one connection to mu. It's the full derivative of U with respect to mu times the full derivative of mu with respect to Zi. But the fulls and partials are the same over here. So I'm being sloppy in my notation, right? And this one over here plus. Now, the full derivative of U with respect to sigma squared times the second term. Is that a full or a partial? What must it be? How many of you think it must be a partial? Raise your hands. How many of you think it must be a full? Raise your hand. How many of you did not raise your hands? Raise your hand. Right? So you guys have to raise your hands. You don't have a choice, okay? One way or the other. Here it is. The question you're asking is, if I perturb Z, how much does sigma squared get perturbed? If I perturb sigma squared, how much does U get perturbed? These are being chained, right? So I can put all of these connections inside a box. The question you're really asking is, if I perturb Z, how much is sigma squared being perturbed? That's the totality of every single influence. So this second term has to be a full or partial. How many of you think it's a full? Raise your hands now. Right? And Parth, you're not convinced. Can you speak aloud, please? I'm speaking, think of it this way. I'm looking at this, and I can put a box, and you really don't know what's happening inside the box, correct? Changing Z changes sigma squared. So when the dependence on mu is going to show up in the derivative of sigma squared with respect to Z. Okay? So everybody with me so far, raise your hands if you're with me. Okay, now, can someone tell me what the partial derivative of U with respect to Z1 is? UI with respect to Zi is? What is it? Here is the equation, right? What is the partial derivative of UI with respect to Zi? 1 over square root of sigma squared, right? Can I hear everybody say that aloud? Okay, you will remember this equation. Okay, so that first term is going to be this guy, right? I can replace it. This is what we have, no biggie, right? So I've changed it. Everyone with me so far? Yeah. So you have a question? So look, that's the second term. This is just the first term, correct? This is the partial. Remember, these are the three guys. This is the direct path. So remember, take a look at the picture. This is how you have to think about it. This is this path. Okay? The second term is this path. The third term is this path. You clear? And so the first guy has got to be just the direct path, right? And the direct path is going to be this one. So everybody clear about where that term came from when I broke it down, right? So now I need so this guy is done, right? Let's focus on this. What is the derivative of U with respect to mu? Can I have everybody say it aloud? What is the derivative of U with respect to mu? Okay, there you go, right? From the same equation. So I can replace that here, okay? The last thing, what is the derivative of mu B with respect to Zi? from this equation, correct? So can you say that aloud again? Okay, just so. So does everybody get where these equations came from so far? Any questions, right? No, okay. Now, last term, what is the derivative of u with respect to sigma b squared? What is this term? So who is number 27? One of you is number 27. Who's 27? Guys, who is number 27? Check your tokens. Yes. Okay, Varun. What is the derivative of u with respect to sigma b squared? Tell me. Which equation would you be using? Pardon me? Can you say that aloud, please? The highlighted one, right? And what is the derivative of u with respect to sigma squared? U was z minus mu times sigma squared raised to minus half, correct? I can think of it this way. Skip the plus epsilon. So now what is the derivative of this with respect to sigma squared? Sigma squared to the power minus 3 over 2. And into z minus mu. And what about the sign? Minus. Everybody's with this so far, right? This is a standard derivative rule, correct? And so this that just comes out to this term. And I can replace that over here. Right? So now I'm left with one last term. The derivative of sigma squared with respect to zi. Is there a second brave person in this room? Okay, all right. Nikhil, you're going to help me. You want to come here and help me? Come along. And you can do it through using the picture, right? Just erase anything you want to and just write it out. Yeah. Now the point is you did a lot of batch norm, and batch normalization was a hideously ugly operation. You did not understand where the mathematics came from. But when you break it down and draw the pictures and actually work through the arithmetic, it ends up being totally trivial, right? So what is it going to be? So let me help you, right? That's the connection. There's the picture. Okay, now right. Now I want the derivative of sigma squared with respect to, wait a minute. So first, this is going to be the derivative of sigma squared with respect to zi. It's a partial, right? Plus the derivative of sigma squared with respect to mu b times the derivative of mu b with respect to zi. Everybody see where this equation came from? Right? What is the derivative of sigma squared with respect to zi? Okay, write it down. Okay. Yeah, so which is going to be? This is going to be 0, right? So this first term is just going to be 2 times. It's a specific zi. Will it be 0? I'm asking the derivative with respect to a specific zi. Okay, and there's a 2, correct? There's a 2. So this first term is going to be 2 times z minus mu over sigma squared, correct? Everybody here with me? Now, so I put that in. What about the second term? What is the derivative of sigma squared with respect to mu b? And what else? Now does the summation go away? Okay, write it down. Speak aloud and tell me. Erase everything And write nice big characters. There are people seeing you from halfway around the world. Okay. Whatever you write has to be visible all the way to Doha. Does anybody else want to tell me what the answer is while he's working it out? Pardon me? There's a very simple answer. Does anybody want to tell me? Was it? It's got to be 0. Why? Yeah, because you have the summation, right? There's a 2. Don't forget the 2. There's a -2, right? This, yeah. So this term, this derivative over here is -2, so 1 over b summation zi minus b, and this term is 0, right? So thanks, Mikhail. Yes, you're right. And so I don't need to bother with the rest of it, right? So the derivative of sigma squared with respect to zi is just going to be this one little guy. And so this, and so the derivative for the through line, I just put everything over here. This is what it looks like. It's kind of ugly. It looks complicated. If I just presented it to you the first time around and asked you to derive it, you might faint. But then when you actually draw the pictures out, there's nothing complicated about it at all, right? Everyone with me? Raise your hands if you got where this equation came from. But that's only for the through line, right? What, you have this other guy. What about the non-through line, the off line? Do you have the confidence to derive those equations on your own as well? No? It's basically the same as the derivative for the through line, right? With first, you have this first term, which was the same as before. You don't need to worry about it. And you have the second term, right? And this is similar to the I equals j without the first through term, right? It has 2 of the 3 terms. That's about it. And if you actually work it out, it's going to be this interesting little formula over here. Nothing particularly complicated. In the through term, this was zi minus b squared. Now it is zi minus b times zj minus b, but that's it, okay? And so here's what we get. The derivative of u with respect to the z's, you get this one formula if j equals I, the other if j is not equal to I. And this formula can directly be plugged in to our mini batch loss derivative. And so when you work your way back, that is going to give you the complete derivative with respect to the mini batch loss. The math, I'm not going to explain the equation. It looks ugly, but it's actually completely derivable. But there's an intuitive process to it. And this is the cute bit, right? The derivative of the loss with respect to any zi is going, remember, you're doing a batch normalization, correct? So here's what happens. The derivative of the loss with respect to any zi is the derivative of the loss with respect to the corresponding ui with the scaling term, okay? And then what is the second term? The second term look familiar? What does it? It's the average of the derivatives for all the ui's, right? So because batch normalization does a normalization, it subtracts a mean, you do the same operation going back in the derivatives as well. That's all you really do. You get this denominator term for normalization, but then it's the derivative with respect to the ui minus the average derivative for the mini batch. Very pretty, right? If you actually sort of skip through the math and look at this equation, it's very pretty. Now there's this third extra term which has to account for the variance. And so this really has to do with, you can sort of intuit your way around this. This is looking at the cross influences because the average doesn't account for everything, okay? And so it's very, and fact of the matter is if you ignored this most times, it would not kill you. This captures the spirit of the batch normalization. And now, so here's the batch normalization. For any given input, you can use these equations to compute the derivative with respect to z, and then you can compute your gradient descent going backwards. And now, before this poll, there's one last thing, and this is to you, Joe. If all of your mini batch had the same instance over and over again, what would happen? What will happen? Remember, I'm computing the derivative for an instance and subtracting it from it, the average derivative for the mini batch, right? What will the outcome be? 0, right? And so also this term over here, this is also just this is a weighted average, that too will become 0. And so if your mini batch consists of the same instance over and over and over again, as you backpropagate, the derivative is just going to stop right there and it's going to become 0. Even if the variation between instances in the mini batch is not very large, you're going to get pretty much the same behavior. The individual derivatives are going to look like the average and it's going to stop. Okay, so this is a problem with the batch normalization. You need diversity in the mini batch at the node for the derivatives to not just die at that node. Everybody get that? Okay, raise your hands if you did. Right. We're getting to the end of the class. So, okay, I gave away the answer, you didn't see. This is an easy one. I'm only giving you 10 seconds. Okay, guys, done. So batch normalization effectively blocks backpropagation and prevents gradient computation if all of the instances in the mini batch are identical or very similar. This is the condition where BN will actually fail, right? So when you're implementing batch normalization, this is something that you want to worry about. So but all of this is during training. It's about messing around with mini batches, right? What do we do during inference time? During inference, you don't operate on mini batches, you operate on an individual batch. Now the gamma, the beta are learnable parameters for every neuron where you apply batch normalization. So those you know. But what does this mean and what are this variance that you're going to be using to normalize the individual training test instances? Test instances don't occur as mini batches. So you need to take some guess as to what these guys are. And so here's where the standard heuristic comes in. You take the average of the mini batch means over all of the mini batches in the training data. And that's going to be the BN mean that you will be applying to normalize your test instances. So also, you're going to take the average of the variances of all of the mini batches. And that's the variance that you're going to be using for normalizing in this equation. This B over B minus 1 is the difference between a biased and an unbiased estimator of the variance. And for whatever reason, we like to use the unbiased estimator because it's more stable. Now, the unbiased estimator, it's when the number of mini batches becomes smaller, if the mini batch size becomes small, then using the unbiased estimator can make a big difference versus using the biased estimator. That's it. And so BN, this is how BN operates. It can be applied to some layers. It can be selectively applied to some neurons. It can be applied. We've shown it as being applied before the activation. You could apply it after the activation, no big deal. The whole point is to standardize all of the mini batches and move them to a common location, which is neuron specific. It is neuron specific, right? And this improves convergence rate and neural network performance. The anecdotal evidence for which I've seen things go either way is that if you combine batch normalization and dropout, things get worse. You can sort of think of why, but this is the empirical evidence at least. To get maximum benefit from BN, learning rates must be increased and the learning rate decay can be faster. Also, we need better randomization of the training data order. So here are some results from Sergeyev and Zegedy in 2015, the first paper that showed BN. So this, I believe, is a number of iterations. And you can see the performance for different networks. And you can see that when they apply batch normalization, different variants of batch normalization get to the same performance level in a fraction of the time because the network actually converges much faster. Right? So, story so far, covariate shift between training and test may cause problems, and this may be handled by batch normalization. Now, I'm kind of out of time. I'll take one, I'm going to go over 2 minutes, right? The figures shown to illustrate the learning problem so far were kind of fake news, right? in the sense that I try to learn this entire function from just a few snapshots of it, right? And what do we do? At each training instance, you have an error, and you're trying to minimize the total training error over the entire training set, which could be, if you were using the L2 loss, this is what it's going to be. But then there's nothing stopping the network from just learning this function, right? The network could, instead of trying to fit the function everywhere, could just fit the function at the specific training instances and completely bar at every other location in the space. So we need additional smoothing constraints that will fill in these missing regions acceptably. Generalization. So I'm going to use a simple binary classifier to illustrate this process. If I have a simple binary classifier, if my blue and red dots are my training dots, I want the sigmoid curve to be the function that the network has learned. But because the network is infinitely powerful, we know this is a universal approximator, correct? There's nothing stopping the network from learning the horrible purple function. So how can we prevent this? And which of these two would you want, the purple or the smooth curve? The smooth curve, right? So an unconstrained model can model the individual training instances and completely get blown up. And that is because you have these very sharp changes, which happen because the perceptrons in the network are individually capable of very sharp changes. And how can you get a very sharp change? Anyone want to tell me? Yeah. A super steep sigmoid. So look at this. Here is a sigmoid, for instance, or any activation, but I'm choosing sigmoid as my example. Now, if the weight is 0.5, the sigmoid is the blue curve, right? If the weight is 5, it ends up looking like the red curve, which is basically a step function. And so if I have a network where every single neuron, it just ends up modeling a step function, it can end up learning this function instead of a smooth one. So what would your solution be to this problem? Pardon me? You want to keep the weight small. You want to say, I do not want the. So you want to penalize large weights to make sure that the weights also stay small. And the way you would do it, you would constrain the weights to be low. And this is going to force perceptrons which rise slower and get a smoother output response. And the way we will do it, this is your standard training loss, right? Conventional training loss. To this, we're going to add an second term, which is the norm of the weights, squared norm of the weights. The larger the squared norm of the weights, the more the penalty, right? And so now you're not only going to try to minimize the loss, you're also going to try to minimize the squared norm of the weights simultaneously. So this augmented loss is what you're going to actually use in your gradient descent. And when we use this augmented loss, I'll just stop right here in a bit. The derivative you get is going to look like so. It's going to see, if you had your standard loss, and I call L hat my augmented loss, that's going to be half norm W squared, right? So when I compute the derivative of this with respect to the L hat, this is going to be the standard loss W plus, this is 1 over 2, oh no, lambda over 2, right? This lambda over 2 plus lambda W. This is the new derivative, right? So when this is the new derivative, then my update rule is going to become W minus eta, this is L hat, which is W minus the derivative of your standard loss minus lambda times W, right? Which is the same as saying 1 minus lambda times W minus eta times the gradient of the loss. Does this look familiar? We call this something in your homework. What did we call it? No, so we were calling this, we're calling it weight decay, remember? You call it weight decay because the weights are getting multiplied by this 1 minus lambda factor, which make it smaller. Okay, and so that basically just gives you the updated rule. Now, there's one final bit. I'll take another minute. Networks have many layers. There's another way of smoothing the function that the network learns. When you have an input, each layer is operating on the output of the previous layer, right? So each layer is going to end up smoothing the function a little bit. And so the first layer may give you this red curve, the second may give you the green one. By the time you get to the output layer, the function gets terribly much smoother. And so just increasing the depth of the network can make the function smoother and make it more generalizable. So here, for example, there's a little example where we were trying to train a network to capture these decision boundaries. We know exactly how to do this, okay? But here's what happens. This is the decision boundary we're trying to learn. In each case, we have 660 neurons. This is what you actually learn with 3 layers of 220 neurons. This is the 4 layers of 115 neurons, with 6 layers of 110 neurons and 11 layers of 60 neurons each. And you can see what has happened as you end up going deeper and deeper and deeper, the same number of neurons connected out into a deep network give you a much smoother representation than when they're connected in a smaller number of wide layers, right? So data under specification can result in overfitted models and must be handled by regularization and more constrained, deeper network architectures. I'll stop right here. I have skipped a lot of the class. I went slowly on purpose because I was taking my time over BN. We will be covering dropout in the evening at 6 o'clock. Again, I'm apologizing for taking up your time at 6, but because we got delayed, I'm just abusing my extra hour, right? We'll cover dropout and the remaining topics. It should not take much time. How was it?